How is that for a Pearson product momentum correlation coefficient, otherwise known as an R value, right? Nothing like a mathematician to reduce 5 words to 1 letter. So we've already discussed that when we find a line of best fit, we're trying to make all of these differences as small as possible. And we do that with a least squares regression line. In other words, those distances are measured, they're squared, and then we're trying to keep that number, when you add them all up, to be as small as possible. Now, if they're really close to the line, we would say it has a strong correlation. If it's not really close to the line, we say it has a weak correlation. But it's nice as a mathematician to have a number that measures that. And that is what the R value does. It measures that. There's an R value and there's an R squared value. So your calculator will calculate this for you. If the line is perfect, then we would say the R value is 1. If the line is perfect in a negative slope, then we would say the R value is -1. Anything that's not perfect is somewhere between that -1 and 1. With 0 correlation, meaning this is terrible, we could draw basically anything as a line of best fit. So, -1 and 1 is what it could be between. 0 would be no correlation whatsoever. A number close to 1 is strong and positive, and a number close to -1 is strong and negative. So here's some examples. Everybody good? Just showing you the difference between these dots really form a nice straight line. The R value for this one might be -0.9. Not as close, the R value for this one might be -0.5. No correlation whatsoever, then the R value would be 0. Positive correlation, stronger, and a perfect straight line was where you would get an R value equal to 1. So we have descriptors for this. We would say that if it's above 0.75, we'll use strong. 0.5 to 0.75, moderate. 0.25 to 0.5, that's pretty weak. And between 0 and 0.25, that's very weak, almost no correlation whatsoever. So it gives us a way of not only saying there is a relationship, but how good of a relationship. Right? And here's the mathematical way of figuring it out. So we've got some of the same similar formulas that we had in the least squares. But for these values, showing you the formulas, how it's calculated, but for the most part, we're going to be using our calculator to get these values for us. So remember that data that we had before. This is those 3 points for that line of best fit. I think we found the line of best fit to be y equals x plus 1. We had already calculated some of this chart, but now we could add to it x squared and y squared. And then calculate each of the things in between. So in those formulas, remember that this sigma sign means sum. So x times y, you do it each time, add them up, you'd get 20. Adding up all the x ones, you'd get 6. Adding up all the y ones, you would get 9. So you can calculate each of these things on its own, and we would get an R value of 0.5. Okay? See if I still have, was this the last thing I put in my calculator? See if those points are still in there. Or let's see if the calculator, it's good to start talking to the calculator, I guess, early in the lesson. Yes. So I'd found those points in there. I had gone to stat and over to calculate, and I found the linear regression. And if you're typing it in, you do list 1 and list 2. If you want to even store it, you could hit your variable button, go to y variables, enter on function. Oh, this is the hard part about the statistics unit. You have to know where all of these things are on your calculator when you're sitting in your test. There are sometimes people are like, I've just been pushing buttons for 5 minutes hoping to find something. So I calculate this line of best fit, and it calculates A to B1, B to B1. Does anyone's calculator, did it say R and R squared on it? Does anybody's calculator already give them the R values? Yours does. Okay, good. So we're going to want to have our calculators tell us our R values as well. To do that, we're going to have to turn our diagnostics on. So if you go second and above the 0 it says catalog, it has every single thing your calculator can do. I have no idea what ANOVA does. This is kind of disappointing because I remember in high school having just a regular scientific calculator, and you could see all the buttons on there, and I was like, one day I'm going to learn what everything does. And now I have a graphing calculator that has way too many commands in it that I've given up. Anyways, you can scroll down until you get to diagnostics, or if you automatically push the letter D, it will jump to D. And if I push diagnostics on and push enter, it'll say done. And now, if I go stat, calculate, linear regression, and calculate it, it not only calculates the A and the B value, but also tells me my R value and squares the R value as well for R squared. So the R value is 0.5, the same that's calculated with here. Is 0.5 strong? Not really. It's kind of almost in between moderate and weak. I would still probably say it's pretty weak. When we look at the graph, does it look like those dots are pretty far away? Yes. Is it a positive correlation? Well, it seems to be going down and then up. I'm not sure. So this is why the R value comes out lower, because it's not a super strong correlation. So put this one into your calculator. Put the math mark into list 1, physics marks into list 2. Do you think there's a strong correlation between math marks and physics marks? Do people who do better in math generally do better in physics? Or is that something there would be a correlation between? And then once you have it, put it on your graph and show me if you got the same linear regression and R values that I did. So our question is also asking comment of the strength of correlation, so it's pretty strong, and then use the equation to find physics marks for a student who scores a mark of 50% in math. Okay, so what you would do is you go to your math marks are your X values, your physics marks are your Y values. So your equation is in there, and you can go to your calculator and you can find a value. The way that you find a value, and I don't have the data in here, but you can, above the trace button is calculate, and number 2 is calculate a value, or sorry, number 1 is calculate a value. Push enter, and you could put in X is equal to 50. Since X are your math marks, you can enter that in, and it will spit out the 53.7% as a physics marks. Where would you expect more correlation? Okay, so math and physics is 1. How about English and history? Physics and history, math and English. Which one do you think would have the strongest correlation? If you're good in one, you're good in the other. History and English. If you're good at English, you're good at history. If you're bad in English, you're going to be bad in history. Or do you think math and physics would be a closer one? I don't know. I think you could argue either one. I don't think math and English would be a very good indicator. Because there are some people who are really good at English and really bad at math. There are some people that are really good at English and really good at math. Right? And there's people that are really good at math but really bad at English. So that one I think would have less correlation than something, because physics and math, they both do a lot of the same things, a lot of formula work, a lot of math work. So you understand that there would be more of a strong correlation there. Interesting. And with that, where are we? We are done the booklet. That is statistics. Statistics is closely related to our next unit on probability, but we are officially done the statistics unit, so I'm going to give you today also to get started on your take-home quizzes.